Suppose we know the velocity of a particular particle moving along a straight line where it speeds up and then it slows down. And let's say we want to try and determine the displacement of the particle. Given we know the velocity, we can determine the displacement of this particular particle along this trajectory. What we could do is we could just consider 1 second time frames and assume that the speed remains constant for the entire second. This would become an area problem. The reason this becomes an area problem is because distance is equal to speed times by time, or specifically in this context, displacement is equal to velocity multiplied by time. And a rectangle is calculated by length times width, and in this case here, a rectangle's length is its velocity given by the graph, and the time is some tiny dt stamp or some nudge along the t direction. And although this is perfectly reasonable to consider 1 second timestamps, as it would give a nice estimation of the particle's movement, what it would really be doing is kind of giving a jagged movement of the particle, because it wouldn't have some kind of a smooth motion. Its motion would look more jagged, where we're assuming the speed for each time interval rather than a continuous speed. To get a better estimation of the true displacement of this particle, what we could do is we could just consider timestamps of smaller and smaller value, or in other words, let d of t approach the value of 0, meaning that we would have infinitely thin rectangles under this velocity curve. The smaller the timestamp, the smoother the movement of the particle, because we're not going to be assuming some constant speed. With infinitely thin rectangles, what we would have is an integral of velocity that would describe displacement, which is really just adding an infinite number of thin rectangles under the curve. If we recall the difference between displacement and distance, the total distance traveled would be in purple, whereas the displacement is the distance from some fixed origin. Consider a new context. Let's say we know that the velocity of a particular particle travels in this cubic function here. And what this would mean is we'd have positive velocity, and then it would move back to the left direction with negative velocity, and then back forward in the right direction with more positive velocity. Calculating the displacement would simply just be evaluating the integral under the velocity function from whenever you start to whenever you stop. If we were to interpret this on a graph, it's kind of like saying green area subtract purple area. But let's say we want to calculate the distance traveled by this particle. What we would need to do is consider the signed area under the curve, which is kind of like saying the green area plus the purple area plus that next green area. This has a direct link with the fundamental theorem of calculus, where if we wanted to determine the displacement function of this particle, what we would do is we would evaluate the integral of the velocity function. Doing this, we substitute in our upper bound and lower bound, and what we would get is a nice function that describes the displacement of the particle. And this plays out exactly as we would expect. The displacement starts to increase as the velocity is moving to the right, then it decreases when the particle goes back to the left, and then once it hits that stopping point again, it starts to increase as it moves to the right. And we can kind of visualize this if we just watch the particle moving once again. It moves to the right, then loses some displacement, and then it further goes forward. Let's watch this play out one more time. And we can use this to further understand the fundamental theorem of calculus. The velocity function has positive y values, so we should expect positive slopes on the displacement function. It's got negative y values on the velocity function, so we'd expect a negative slope on the displacement. And then further, more positive y values give us an increased slope. And this is behaving exactly as it should, because if we've got positive y values on the velocity function, the area underneath it must be positive. And if we've got negative y values on the velocity function, the area must be negative. So this kind of verifies our idea of the fundamental theorem of calculus, where the displacement is the antiderivative of the velocity. Particles moving in a straight line and its velocity v of t is measured in seconds, and it's given by some linear function here. So this guy here. It says, find the particle's displacement after 4 seconds, given the particle was initially 2 meters to the right. Okay, we can do that. That's just a bit of integration. As we've seen, if we know velocity, we can determine the displacement by integrating. It wants us to find the distance traveled. Okay, I'm going to highlight that one. The distance, so that's the signed area, as we saw, and the first 4 seconds. And then we're going to sketch a velocity time graph and really analyze our solution. So let's start with the first one here. The displacement is equal to the integral of velocity. Okay, so I can evaluate an integral here, and it's saying, given the particle was initially 2 meters to the right of the origin, so that's going to tell me when t was equal to 0, d of 0 was equal to positive 2 because it's to the right. So that gives me a coordinate of t being 0, y being 2. And I'm going to substitute that into my displacement function. Okay, and so that is our initial condition, and as expected, we do get a nice displacement function where the constant was equal to 2. And so if I want to find the distance traveled of the particle, what I'm going to need to do is I'm going to need to consider the signed area. And when I'm doing this signed area business, I'm going to give myself a little sketch. Okay, and if I want to calculate the distance, what I'm going to need to do is I'm going to need to consider the signed area. So that's all of this stuff. Let me shade it in a light purple here. I'm going to have all this negative area. I'm going to have to take the positive of that, and then I'm also going to consider this area above the curve for the first 4 seconds there. So the way I can construct this is I know that it's got a x-intercept at x equals 3. So that's my x-intercept, which kind of splits up my integral. So I can say here that the distance is equal to the negative of the integral, because this purple area here is going to give me some negative number. Okay, I could actually just calculate the triangle, which I might do to verify. Okay, because this triangle has got a height of, I suppose you could call it -6, but I'm just going to call it 6, and a base of 3. Okay, or vice versa. So I know at least, I might actually do it here, that the area is going to be 3 times 6 over 2, so that should give me 9 units squared. Now it's actually going to give me -9 units squared, but I want this integral to give me a positive number, so that's why if the area is under the curve, I need to consider this negative sign that's there. And I'm going to take the integral of this function here. And then I've got this last part to consider, and I'm doing that from 0 up to my intersecting point of the x-intercept there at 3, and then I've got this next triangle there, which again I might calculate the area of that. It's got a base of 1 and a height of 2, so I'd say it's 1 times 2 over 2, which is going to give me 1 unit squared, and that should be the total distance. Okay, it should be 10. All right, but since this is positive, I'm going to have plus the integral from 3 to 4 of 2t minus 6 dt. So when I evaluate this signed area, I know I should get 10 units squared. Okay, now as all lessons are learnt, let's take our time with this stuff here. So I'm going to take the negative of all of this, and I'm going to put in my upper bound, which is 3. I'm going to say 3 squared, subtract 6 times by 3. And all of that, subtract the lower bound, which is 0 squared, subtract 6 times 0. And this here is representative of that. And it's important to have your brackets there. Otherwise, you might get caught up on some of your negatives, and you don't want to do that. And then I'm going to add this next one here. I'll do it in a green. This next lot here. Okay, and I'm just going to slowly evaluate this down. So here I've got the negative of 3 squared is 9, subtract 6 times 3 is 18, and I'm going to subtract that away from, so this is the negative of all of this stuff, subtract that away from 0 squared is 0, subtract 6 times 0 is 0. And then I'm going to add all of this stuff. The first guy here is 4 squared is 16. Subtract 6 times 4, which is 24. Minus 3 squared is 9. Subtract 18. Furthering this, 9 minus 18 is negative 9. Subtract 0. That's just going to leave that as so. And then plus this here, I've got 16 minus 24. So it's going to be negative 8. And then I'm going to have a subtract away 9 minus 18, which is negative 9. And I've got here a negative of 9. Negative of negative 9 is going to be 9, as expected. So just pause if... Can this zoom out? Oh, thank you. As expected, this here should have been 9 units squared, because this was representative of this area in there, which we found was 9 units squared, which is great. And then we're going to a plus negative 8 minus minus. That becomes a plus. So that's going to be plus 1, which is equal to 10 units squared. And that's exactly what we expected to happen, which is very nice. So remember to take your time with this process here. Third part of the question, sketch the velocity time graph. Okay, we've done that. The signed area enclosed by the graph and the t-axis. Okay, yeah, we've done that. And yeah, cool. So we've found the area enclosed. So the signed area is what we had. That we already figured out. That was 10 units squared. And then the area under the curve, we might actually just finish this one off here. The area enclosed by the graph and the t-axis would just be going from 0 to 4 of our velocity function, where we just want to consider the total displacement, whether it be positive or negative. Now, moving ahead, we know we've got negative 9 plus 1, so we're going to expect that answer to be negative 8, but let's just zoom through and verify that our integration works. Okay, and as expected, we got our negative 8 units squared.